So this problem states that we have 100 meters of fencing to make a rectangular enclosure against a wall, and it's asking what dimensions maximize the area. So when we do an optimization problem, the first thing we want to do is identify which variable or component that we are maximizing. So here we are maximizing our area. And we're given the information that we have 100 meters of fencing to make this enclosed area happen. And we know that this 100 meters must be related to the area because the more fencing you have, the more area you can enclose. So let's draw a diagram to help better visualize the situation. So it states that we're making this rectangular enclosure against a wall. So here, we're going to assume that is referring to an enclosure that's boxed off. So we'll have this green represent the wall and the red represent the enclosure material. So that means we just have three sides enclosing here, and that is our 100 meters of fencing. So we'll call this X and we'll refer to this as Y. Okay, so we're maximizing the area. That's what we identified. When we do our optimization problems, we want to write an equation that pertains to that maximized value. So here we can state that area is equal to our X, our width, times our length. And when we do optimization, our eventual goal is to find the derivative of this maximized value of area here, in this case, and set it to 0. Set this area to 0 after we find the derivative, because if you'll recall, when we have a function and it's a continuous function, at a local maximum or a local minimum, the slope or derivative will be equal to 0. So we want to find that point where it's maximized. We want to find where the slope is equal to 0. But if you'll see here, finding the derivative is a little bit more convoluted. We're going to have to use the product rule and things will get more complicated. So the easiest thing to do in this scenario is use that information that we're given in order to make a substitution. So we know that this red area can only be composed of 100 meters, which means that 100 is equal to 2x plus our y. Now we can solve for y here, so we can plug it into the equation. So 100 minus 2x is equal to y, which means that our area is equal to x multiplied by 100 minus 2x. And we can expand that to 100x minus 2x squared. Finding the derivative of area, we get 100 minus 4x, and I'm just denoting the derivative by a prime. That's the same as dA over dx. So now, as I mentioned before, we want to set this equal to 0. 0 equals 100 minus 4x. That gives us x is equal to 25, but it's asking us for the dimensions, plural, so we need to solve for y as well. Well, it's a good thing that we have our initial equation available to us here. So we're able to do 100 is equal to 2 multiplied by 25 plus y, leaving us with y equals 50, meaning that the dimensions to maximize the area include one length dimension of 50 meters and this width dimension of 25 meters. And that's an optimization problem.